Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a specific formula or application of integral calculus and trying to derive the volume of a sphere. And this is going to use the concept of a curve that we had talked when we were trying to talk about the concept of an integral. So we are going to play around with the concept of a surface area volume of a sphere and try to look into different perspectives of trying to find the volume of a sphere. Of course, one of the ways in which we're going to do that is using the concept of pyramids, and that is going to guide us into using the concept of integral calculus and trying to derive this particular formula. So for that case, without further ado, I welcome you. Let's begin. So as I've said, our main point of focus today is trying to find volume of a sphere. And in this case, a sphere is one of the regular, I call it regular figures. Of course, it's a three-dimensional space that has got a centrally located point and the other points which are equidistant from the center. So let's say this is a point, and so therefore we can define a sphere as a three-dimensional space that has got points which are equidistant from the center. So in this case, we're going to look into that, but our main focus is trying to find how to try to derive the volume of a sphere using different methods. Of course, one of them that we said is application of integral calculus, and try to see whether it is going to lead us into that particular concept. So in this case, of course, we're going to use two different approaches. The first one I've said is trying to look at the relationship between different parts of a sphere. And using that relationship, of course, we're going to look at the concept of volume using pyramids. And then, of course, lastly, we're going to look at how to derive this volume using integral calculus. And now, in that case, we will use what we call the disk formula. So these are going to be our main areas of focus. And in trying to see the relationship between the different parts of a sphere, that is going to, of course, give us a clue on how we can be able to use different approaches in deriving its formula as a formula for the volume. So let's try to look at some basic concepts that are going to assist us in trying to figure out how we can find the volume of a sphere. So the first concept that I'm going to use in this case, of course, is trying to figure out what a sphere is. And I'm going to use that one, to do that one using an illustration, of course, which is going to be this particular illustration here. So as I said, this is a three-dimensional space. So therefore, suppose we have a centrally located point at that part, and there's another one, there's a distance r, and there's another point at that. And of course, let's just extend this one. This is the center of the sphere, and this is another point q. We can define, and then we just put an additional one. Maybe when we are talking about circular motion, we talked about circular displacement. Let me just write S, or just C. I'll give a definition what that term C stands for, and then I'll just try to shade that part of the sphere that appears in the middle. So this one I've done it intentionally so that it can assist us try to define some of the concepts that are used here. So first we have distance r, which is OP. Now this one refers to what we call the radius. And then we have distance QP. This one refers to what we call diameter. And then we have the distance that is prescribed using the red color code. That one refers to the circumference. Of course, bearing in mind that that's just a circle, single circle around the sphere, of course. Now, this circumference can as well be prescribed using this dotted line here, together with this particular part of the curve that is going from E to A. So that one is similar as well to going around the circle. So that one revolution is what we refer to as the circumference of that particular circle. Now, with that, in that respect, we are going to see that if there is a plane that cuts across that shaded part that I've written for the circle, then we are going to have a figure that appears like this. Of course, I'm going to just limit its size. We're going to have a figure that looks like this, whereby the central part appears like this, and then this is the origin. Now, in an actual sense, that plane cuts through the center that makes up the PQ. This one will separate this sphere into two parts. Let's call this one part A, and the one that is of course dotted, part B. So part A and B form what we call hemispheres. So in this case, part A and B forms hemispheres, and the circle, the point of contact of the circle, or the area of the circle, which is shaded of course in red, which is cut using that plane, is what we call the great circle. So this circle that formed by the diameter QP and radius OR is what we call the great circle. So finding the circumference of that great circle, which is okay, the great circle will be equivalent to the circumference of C. So finding the circumference of that great circle, it will be given as pi or 2 pi r, and of course trying to find what we call the surface area of this circle. Of course, we know the common surface area for the circle. It is going to be 4 pi r. Area, that is 4 pi r squared. And we're going to see that the surface area, this is for the circle. Now the surface area for the great circle will be pi r squared. So if you look at the relationship between these two, this is the surface area for the sphere. This is the sphere. I've just quoted the surface area for the sphere and the surface area for the great circle, with an intention of trying to show the relationship between the surface area of the sphere and the surface area of the great circle that I've inscribed in that sphere. So the relationship between this surface area of the great circle and the surface area of the sphere is that surface area of the sphere is 4 times the surface area of the great circle. So that's the first relationship that I want us to have a keen interest on. So in this case, we are going to see also that this relationship, of course, is going to assist us somewhere. So we'll just keep that one in check. Now let's try to look at a different concept. Now when I'm going to talk about the surface area of the sphere of the great circle, we'll be having that one in mind and what it implies. So let's try to look at a different concept, of course, that still pertains to volume. Now suppose we have a circle, or suppose we have a sphere that is of that nature. I'm going to use a different concept of pyramids. And for us, of course, we know that a pyramid, maybe we can just remind ourselves, a pyramid is a 4-sided figure that has got an apex at that particular point, and from this center to the apex, that one forms the height of the pyramid, and the shaded part forms what we call the base. So this is the height, and this is the base. So the volume of a pyramid is given as a half base. We use this one to denote base times height. So therefore that's a volume of general representation for volume of a pyramid. Now suppose we have a sphere which we can represent the great circle at this point. Suppose we have a sphere of this nature and we have a particular pyramid in a way that the vertex of the pyramid is located at the center of the sphere. Now the height of that particular sphere, sorry for that, the height of this particular sphere is going to make up the radius. So the distance between the center of the sphere, okay, let's call this one our point P. The distance between OP will be the same as the distance from the base of the sphere, that is of course inside the pyramid to the center. So therefore the H in our case here will represent the radius of the pyramid that is inside the sphere. So over essence, if you try to look at the bases of this pyramid, and a number of pyramids of course are used to form that particular sphere, therefore the bases of the pyramids will form what we call the total surface area of the sphere, which we have given as 4 pi r squared. So in this case, I'm trying to give a relationship between the concept of the surface area of a sphere and the surface area of the bases of the pyramids. But suppose we wanted to find the volume of this particular sphere, then we will have to exploit this concept of the volume of a pyramid, which is a third BH. Now suppose there are n number, just n representing an integer. Suppose there are n number of pyramids which are making up the total volume of that particular sphere.